share.
Right.
Okay. You see my presentation? Hello?
Yes, it is visible. Very good.
Okay. So I'll be presenting, thank you for the opportunity of speaking in this conference. I'll be presenting results that we published in a paper of last year. So it is a dense paper. We reported the presence of magnetic, hot and bright spots in a very particular stellar population, which is called the extreme horizontal branch stars that I will refer to as EHB stars. And finally, for the bigger picture, we propose that they form some kind of a bridge between the main sequence young stars and the white dwarfs. So it is legitimate to ask why one would speak of an extreme horizontal branch star in a conference that is dealing with OBA stars. And the answer is very simple, is that in order for us to understand what our results were, I mean, how to justify them and explain them, we ended up making frequent parallelism to whatever is happening to chemically peculiar magnetic B and A type stars. So let's go directly to the second slide. So I'm presenting a theoretical HR diagram in which one can appreciate immediately that the horizontal branch is really a horizontal evolutionary sequence. So all these stars in here are basically reflecting the fact that they have the same core mass of 0.5 solar masses. And the dispersion in color, which is enormous, we go from 5,000 degrees up to 50,000 degrees, is basically reflecting the function that it all depends on the thickness of your envelope. So following the red giant branch, in which a typical star in a globular cluster would lose up to 30% of its mass, following that at the red giant branch tip, if your envelope is thick enough, you will end up at the red side of the horizontal branch at 5,000 degrees. And as it gets thinner and thinner, you end up being basically, you end up basically seeing the core of the star. So EHB stars would, in globular clusters and SDB stars in the galactic field and the galactic halo, basically have extremely thin envelope masses between 0.01 solar masses and 0.02 solar masses. So these stars are basically doomed to, let's say, skip the programmed evolution that they should have. They should have gone through the EHB asymptotic giant branch and then the planetary nebula and so on. These stars will go directly to the white dwarf evolution. So how do you lose so much mass on the red giant branch and end up somewhere here? So, hello. Okay, so looking at a generic Gaia color magnetic diagram, the first thing you will note that the horizontal branch is not horizontal anymore. So these are the extreme horizontal branch stars. There's a color saturation due to the optical filters that one uses, and this is the extreme horizontal branch stars that we are interested in. Now, interestingly, if you talk about the Milky Way SDB star, sub-dwarf of B-type stars, they have a very, let's say, very straightforward solution for why they come to lose so much mass. And the answer is simply binarity. Up to 2/3 of them, 70 to 80% of them are binaries. So it is very easy to explain that a heading companion will trigger and accrete, let's say, the material from the envelope of the EHB stars. And so it goes. The very interesting thing as well is that when you go to globular clusters, the situation is completely at the opposite. There is a so-called dearth of binaries. There were many groups that tried to monitor spectroscopically the horizontal branch stars in many globular clusters, and they all converged to the same results. Basically, there is a dearth. So far, we have knowledge of only one single EHB system in which you're supposed to have an extreme horizontal branch star plus a main sequence heading companion. So again, if not binary, then what is exactly the situation for globular cluster? And this is why, just to show you the level of complexity that you see that a globular cluster would offer you when you look at the extreme horizontal branch stars, all at the same distance and same age and so on. So you can see this is the red horizontal branch star, and then becomes the blue. And then you start seeing lots of crazy things like jumps, and separation between the subpopulations. So this is the population that we are interested in. It is somewhere between 20 and 30,000 degrees, 0.46 solar masses. And the very important thing, the distinctive characteristic of these stars is that they are chemically peculiar. And this is already a hint of what I will be talking about with respect to the chemically peculiar stars of B and A type stars, because these stars show up to 10 to 20 times enhancement in iron and other heavy elements. And at the same time, they will show depletion in between 5 and 10 times of their helium with respect to the cluster, let's say, the cluster value. So lots of crazy things are happening here. And in order to understand that, we kind of approached the problem by doing a monitoring survey. So directly to our results, we did an ultraviolet and optical monitoring of 3 clusters in order to confirm the results directly. And as you can see, we did recover the pulsational variables as SX Phoenicius and R Lyra in all 3 clusters. But most interestingly, we did recover a new type of variables, new variables in basically the extreme horizontal branch star situation. So extreme horizontal EHB segment. Now, one would ask, what is the big fuss? Because as you can see in here, we already plotted the pressure and gravity mode oscillation instability strips in here. And one would say, okay, so they could be easily, let's say, pulsated. But and in this sense, let's say, pressure mode pulsators are known to display periods of around a few hundred seconds, whereas gravity modes display it up to two hours. So pressure mode again and gravity mode, as you can see in temperature, since we are dealing with stars with EHB stars variables from 20,000 degrees to around 36, we are basically overlapping with them. So it is legitimate to ask if our variables are basically pulsators. But we tend to dismiss this very quickly and very easily by looking at the folded light curves of our ultraviolet filters. And as you can see, the periods of all our sinusoidal single wave variables are basically on the order of days, 3 days, 5 days, 26, 50. Then you go to the other cluster, 11, 5, and the other cluster, 19 days, and so on. So pulsation is dismissed quickly based on the photometric periods. How about binarity? So as I said from the beginning, binarity is by definition excluded in the extreme horizontal branch stars, yet in globular clusters, yet we did our exercise, and for this star in here, which displayed a 0.2 amplitude variability in the U filter, we monitored it with flames at UT2 for 3 nights, which matches its photometric period, and we did not find any significant variability of its VRAD velocities. This is an R Lyra just taken for comparison, just to confirm the goodness of our results. We did it again for another cluster, and the results is basically the same. So we dismiss both binarity and pulsational properties. So first summary of the talk is that we do recover a periodic single wave sinusoidal variability that has a U filter amplitude between 0.05 and 0.2, and in a precise let's say regime of variability between 2 and 50 days. Now, having excluded pulsation and binarity, we end up by exclusion to invoke the parallelism to, and that the variability is to be labeled as alpha-2 canonbenetic quorum, which is basically due to stellar spots that reflect the presence of inhomogeneities on the surface of the star, either enhancement or depletion of certain elements. And as the star is rotating, the projection of which comes into the, let's say, the line of sight of the observer. Now, there are 2 fundamental properties if you expect to detect stellar spots in chemically peculiar B and A type stars. One is that they are kept stable, which is unlike what you would expect for the solar spots, which last until a few months, whereas in here for alpha-2 CVNs, you expect them to be lasting to be stable on the order of decades. And second, then you expect also to detect some kind of a wavelength dependence of these stars. Now, so I have to skip because I'm taking so much time. Okay, so this is just to say that the chemically peculiar magnetic stars are stable on long time periods, and this is just to say again from models from Cook data that the spots on these stars are expected to show are basically expected to display some kind of, let's say, dark spots in the far ultraviolet, and then you have a bright spot in the optical and near ultraviolet, and their effect is less as you go with longer wavelengths. So we did this exercise. This is a 6 years light curve data for one star that had a period of 19.5 days. Then we separated it in 6 years separately, independently, and we did not find any differences in amplitude or phase or anything. So this spot on this star is very stable on long time scales. The same thing for comparing the amplitude of R filter with respect to the U filter, we did confirm also this wavelength dependence. So how do you create a magnetic spot in a chemically peculiar star? I will leave that to the talk of Dr. Cantiello. All I want to show from here is that for stars of interest of our temperatures, which is between 20 and 30,000 degrees, you expect these stars to have radiative envelopes, and just below it you have the helium-second convection zone, which is basically dynamo generating a magnetic field that comes up. So I will leave this to him. And this is why we came to a point where we were so confident that the attribution of the variability that we detect to alpha 2 CVN is correct, because on the left side you would see the models by Cantiello et al., Cantiello and Braithwaite for, let's say, between 7 and 20 solar masses main sequence stars, and on the right side you see Swigert et al. Modeling of the extreme horizontal branch star at a completely different metallicity and so on. And you can see that they are quite specular. So this is basically what allowed us, these are other modeling of Brown et al., basically the same. And we come to conclude that the capability of radiative envelope main sequence stars to dynamo generate magnetic fields can also be extrapolated to extremely horizontal branch stars of extremely small masses and so on. And then this would trigger photometric and chemical peculiarities in iron and helium, and the photometric variability itself. A consistency check, if we convert the photometric period of the star of our variable to a VSNI value, it comes perfectly in agreement around 6 kilometers per second to whatever is found in literature. So once again, we have confirmation of this. So the spots we are detecting on extreme horizontal branch stars are bright and hot, long-lived, and they are much larger than the one would see in the sun. Unfortunately, I will have to skip all this. So the end result, the bottom line result of our paper was that weak magnetic fields of only few hundred Gauss do trigger observables that one can use to explain all the anomalies, chemical or photometric anomalies that one can detect. So very quickly for the bigger picture. So we made comparisons, parallel comparisons with of the EHB stars with the main sequence stars. So what about the SDBs? And do we expect to find alpha 2 CVN variability in CVN in galactic SDBs? The answer is very much yes. The only problem there is that you have binaries, 80% binaries. So for you to detect such low-level amplitudes, you need to go to the 20% that are single, and then there you find it. You search for them, and we did find one convenient case, one good case, presenting of an SDB star with test monitoring showing a 0.2 periodic modulation, which perfectly converts to VSNI value that is in agreement with the literature. Most important thing about this star is that it was studied by that its magnetic field was studied by two groups, by Landstreet, who is also a speaker, and Banyulo et al., both confirming and setting an upper limit of 400 Gauss for this star. But what is really important in here is that the test monitoring offered us a possibility to detect a superflare for this star, superflare with 10 up to the 35 energy, and this allows us to say the following: regardless of the fact that you detect the magnetic field or not, this star does have one, and it has let's say a good spot in it. So the other part of so we made comparison with SDBs and main sequence. So what about main sequence? And very much interestingly, the main sequence stars, regardless if they are the white dwarfs, regardless of their hydrogen or helium dominated atmosphere, at a certain temperature from here onwards, they all become radiative. So just like the EHB stars and the galactic and the SDBs. So once again, we looked for some kind of a Trojan horse in which we tried to extrapolate our results for the white dwarfs, and we did find GD394, who deployed using far ultraviolet monitoring did find evidence of a dark spot in the far ultraviolet, responsible for 1.1 day photometric variability. And their results were, I mean, their conclusion was that this star must have a spot there. So once again, the extrapolations of our results do seem to be agreeing with between the main sequence stars and the white dwarfs in here. Just very much recently, Nicole Riddle et al. Studied a particular type of white dwarfs, very much having the same temperature of the SDB stars that you see here. And for that particular class of white dwarfs, they did detect a very high frequency of variability. And interestingly enough, the variability that the modulation that they see is, let's say, single wave and so on, and with a photometric period which is rather high. They did also the same exercise of excluding binaries and so on, and they converge on the fact that there must be spots on these stars. So we are pretty sure also that we have the, let's say, we extrapolate that the properties that of magnetic EHB stars can be also extrapolated to those hot white dwarf with radiative envelopes. Now, one would say, okay, I understand that they have the same temperature, but we are used to calling white dwarfs as extremely magnetic, displaying magnetic fields reaching up to hundreds of millions of Gauss, whereas we have set a 400 Gauss upper limit to let's say the expected magnetism that we see in extreme horizontal branch star. So this might seem inconsistent, but as soon as you take into account the shrinkage factor that is almost 45, a factor of 45, when you go from the radius of almost 0.5 to a 0.01, which is the white dwarf, you end up that this modest field can translate into almost 1 million Gauss. So this is the end result. This is, let's say, the bigger picture for when it comes to magnetic fields, magnetic white dwarfs. Magnetic white dwarfs, in general, it's customary to consider them as the direct descendants of the chemically peculiar BNA type stars. And there's also this would put them, let's say, this would allow them to the magnetic fields in them are considered basically fossil, but there is also the discussion whether there is some kind of a dynamo-generated magnetic fields population within these white dwarfs. And this is where exactly our results of extreme horizontal branch stars displaying low amplitude magnetic fields can play and in this population, because you're talking about low mass single stars that are extremely old, above 10 giga years, that are almost ready just to become white dwarfs. So the results for the extreme horizontal branch stars should be taken into account when you study also magnetic white dwarfs. And I'm done. Thank you.
Yeah, thank you, Yazan.
Thank you.
And we have one question in the chat by Simon Murphy.
Okay.
What's the source of the figure on slide 14 with the wavelength dependence of the A2 CVN spot brightnesses?
This one here?
If it is number 14 of your slides, then yes. What is the origin?
So the origin is a bright and hot spot that is basically, so since we know, let me put this. Okay, so around this temperature.
Pardon me, what's the source? Probably
the
needs a reference or what?
Okay, so the source is this. You have, according to, let's say, a theoretical modeling by Cantiello et al., they would argue that the helium second convection zone that is just below the radiative envelope. So this is also an answer to the question that you formed before in the previous talk. So these would generate a dynamo, a magnetic dynamo, and then via Beyoncé, this can be brought up to the surface. And just to be, I mean, Dr. Cantiello will speak of this very easily later, but this is basically the mechanism. And what we showed here is that at around this temperature here, there is this lots of chemical and photometric and variability that all just unset. It is this layer, convective layer, that is somehow responsible. It does not come up to the surface. It just remains just below. So the envelopes are always radiative.
Yeah, we have another one question by Dominic Baumann. Can you please elaborate on why pulsations on EHBs are excluded? Okay, I'm sorry if I made it very easy, but it's not. So this is the pressure mode, and these are examples of pressure mode in SDBs. So they are the EHB counterparts in globular clusters, and these are the G modes. And you can look, you can see quite easily that these are high frequency. So you have a period of few hundred seconds, whereas in here you have up to two hours. So when you see this, you do expect to find in globular clusters, we do see pressure mode variables. Brown et al. Did detect it in one of our clusters, but you don't see this. But regardless of the presence of G mode stars have a period of up to 2 hours, let's say 3-4 hours. And this is not compatible with 26, 56, and 11 days that we are finding. More or less, also, please remember the fact that these stars basically are almost naked white dwarfs. They don't have the envelope is almost inexistent. It's 0.01 solar masses. You're talking about the upper 1% of the envelope. So there is, they are so rigid, they cannot transmit all the pulsation that one is used to find in the pressure and gravity modes. Yeah, in addition to the question by Simon Murphy, it was about the quotation, the origin. He meant paper. From which paper does the figure come from?
From which paper does?
Yeah, on slide 14. The first question, it was about the reference.
Okay, 14. Okay, this is Krichta et al., 2018.
Thank you.
Yuri Krichta is also a speaker, I guess, or at least a chair, I guess. And so basically here, he took a solar spectrum and then he induced, he forced the enhancement of elements as you would expect in, let's say, chemically peculiar main sequence stars. And then he subtracted the two. And when you subtract the two, you end up with a spectrum that is negative in the far ultraviolet region. It depends on what filters you have. You can put, let's say, shade with other filters, but the end result is that somewhere around the near ultraviolet and the B filter, you have a higher contributions, you have a higher flux. So you will end up having the bright spots that we are detecting. But if you go to the R and I filter, you have lesser amplitude, which is exactly what we see here. So this is the U filter and this is the R filter. And this is, let's say, the plateau in which we know that this star is going brighter as the spot is coming into the line of sight. And the amplitude is larger in the U filter with respect to the R filter.
Yeah, and there is one question from Svetlana Hubrik.
Yeah.
How the typical spectrum looks like? Which elements can you identify?
This is the point which is very difficult. If you study galactic SDB stars, then you can find lots of elements in. I'm sorry, I don't have one in here. But when it comes to so SDB stars, a galactic field and the galactic halo SDBs are very close. So you can really, with an 8-meter telescope, you can really see lots of, as you go to very far away clusters like 8 kiloparsecs and so on, like the studies, like the clusters that we have studied, it's basically impossible to see other than hydrogen and helium, basically. And the only way, sorry, I can show you this. So this is reflecting HST spectra by Brown et al. Of stars in this region. So, and in there, he could manage to detect all these elements in here. But you have to take the HST for that. Otherwise, from ground base, even with an 8-meter telescope, it's other than hydrogen and helium, maybe you can see calcium HK and so on, but not much.
Yeah, thank you very much for the very nice talk, Yazan.
Thank you very much.
And the organizing committee asks me to remind the speakers that presentation should be switched off after the questions.